we already know how to add, subtract, multiply, and divide, mostly from when you were in elementary school, but now you know how to do all of those things with functions. The last operation that we can apply to functions is something called composition. No, you are not composing music, although we can briefly, if that makes you feel better. That's a terrible note. Anyway, composition of functions, composing functions together, is kind of a way of substituting a function inside of another function. So just like on the last lesson, we can write this as f of g of x. Again, you're not multiplying right here. This is a circle representing composite. So we can say f of g of x, which is the same thing as f of g of x, which is f of g of x. Really what it means is that you are taking g of x and you are plugging it into the function f. Okay? Again, one of my students used to say that things would get foggy when she composed, but really if you think of it as substitution, things should go okay. We started talking about functions using these circles with our inputs and outputs. So if you remember, our inputs is everything that we call our domain, and our outputs then is everything that we call our range. So if I were to take x and apply function, we'll say k, all of my range values then are called k of x. I think we're all good with that concept. Well, composing functions means taking a function and then putting it inside another function. So I'm going to start with that domain. I'm going to apply function k. Let me get back k of x. And we call this, what color did I use up there? Oh, I kept it red. This was the range of k. But now, I'm going to use whatever the range of k was, and I'm going to apply, we'll say function j, and create some new values. J of k of x, because that's what I put into my function j. And this is now the range of j. So the domain of k gets turned into the range of k, but then this becomes the domain applying j, creating this new range. So really what I've done is I've taken x and I've applied j of k of x. Okay? It's kind of like hopping different circles, and you can do this many, many, many times over. We're going to stick with just 2 or 3 at most for right now. Alright, so given f of x and g of x, we want to find f of negative 3. This should be a pretty quick review for us. F of negative 3 means wherever I saw an x, I want to replace it with a negative 3. Apply order of operations. Negative 3 squared is 9. So f of negative 3 is 9. You could also write that as the point. Negative 3, 9. Alright, well this next one says f of g of negative 3. We're going to start on the inside, just like we always did when we applied our changes to functions. And I'm going to take negative 3, I'm going to put it inside function g. That's all I'm going to worry about for right now. So that means that everywhere I see an x in function g, I now want to see a negative 3. So 3 times negative 3 is negative 9, minus 1 is negative 10. So g of negative 3 is really negative 10. Well, that means that I want to take f of negative 10. How do you take f of negative 10? Inside function f, everywhere you see an x, you replace it with a negative 10. So our final answer is 100. F of g of negative 3 is equal to 100. F of g of x, you're going to start on the innermost function. You're going to apply put x into function g. Well, here's g of x. Here's g of x. G of x is equal to this. So I'm going to substitute in, and I'm going to say that's the same thing as f of 3x minus 1. I just substituted 3x minus 1 for g of x. Well, now we've practiced this many times over. I'm going to take 3x plus 1 and plug it into function f. Wherever I saw an x, I'm replacing it with a 3x minus 1. And squaring it. So you can FOIL that out. You'll get 9x squared minus 6x plus 1. Final answer, although I would accept that answer as well. Last one, g of f of x. I'm going to start on the inside most, which is f of x. Well, f of x is listed right here. And f of x is the same thing as x squared. So this is really just g of x squared, which means up here in function g, everywhere I saw an x, I now want to see an x squared. Final answer. You are just substituting in one function into another. Alright, you do not have this slide on your notes, but just something I want to talk through real quick. So I've got my two functions, f of x and g of x up here. I'm actually going to use red for that one. If I take f of g of x, that means I'm taking g of x, and I am plugging it into f of x. Simplifying that, I end up with 1 minus x, if you were to actually square that square root. Okay? So it says using the same idea, find the composite g of f of x. So we're going to replace all of our x values in g with an f of x. Well, what was f of x equal to? It was equal to x squared. So inside function g, everywhere I see an x, I now want to see an x squared. Now it says find the domain of the composite. Well, domain is all the values that you can put in to this function. If you think back to this concept though, your domain here was dependent on your domain here. So we actually need to consider a few different domains happening. So starting back with our original function x squared, is there anything that you can't square? No. So f of x had all real numbers. G of x had a restriction on it, and that restriction was we've got a square root, and we know that whatever is under the square root has to be greater than or equal to 0, which means that 1 is greater than or equal to x, also meaning that x is less than or equal to 1. So there's our restriction for g of x. Now let's look at our restriction for this whole composite. Well, this composite still has a square root, so whatever's under that square root has to be greater than or equal to 0, which means that 1 is greater than or equal to x squared, which means the square root of 1 is greater than or equal to x squared. Not quite how that works. You want to think about it in terms of a polynomial. 1 minus x, 1 plus x is greater than or equal to 0, which means that we need x to be greater than or equal to negative 1, and x to be less than or equal to 1. So of all of these restrictions, how can we piece all of these together? Well, we can't say all reals because we have other restrictions. We can say x is less than 1 because it's also less than 1 here. Sorry, less than or equal to 1. And then we also have to include this restriction as well. So x also has to be greater than or equal to negative 1. Pick any number in between negative 1 and 1, plug it in. You should be able to get a real answer back out. No imaginaries. One of the coolest things about composites, yes, there are cool things about composite functions, is they can definitely be used to represent some real-life situations. So the graph at the left shows a swimmer's speed as a function of time. The graph at the right then says the swimmer's oxygen use dependent on that speed. So we've got our two different functions. Some basic questions to ask first. What is the speed after 20 seconds of swimming? So after 20 seconds of swimming, our speed speed looks to be about 1.5 meters per second. What is the oxygen consumption when he is swimming at a speed of 1.5 meters per second? Well, here's our speed of 1.5 meters per second, and our oxygen use we're going to say is about 10 liters per minute. What is the oxygen consumption after 50 seconds of swimming? Well, our input is seconds, so we're going to go to our x's, which are seconds, go to 50. Then we're going to find our speed. But I don't want to know the speed, I want to know oxygen consumption. Well, using the speed of 2.5, I can then jump to this graph, 2.5, and find my oxygen consumption was 25 liters per minute. How many seconds have elapsed if the swimmer's oxygen is 15 liters per minute? Well, we want oxygen use to be 15 liters per minute, which means the swimmer is swimming at 2 meters per second. When was the swimmer swimming at 2 meters per second? After 30 seconds. So it says, what does the function g of f of x represent in a real-life context for the swimmer? So, thinking about starting with the inside out, what does our first x represent? What's the first input we have? Well, the first input we have is time. Then after time, we apply function f, which gets us to speed. And after we know speed, that turns into oxygen use. Which means really this whole function, thinking about those circles and how we jump function to function, really the function in its entirety is oxygen use based on time. Ooh, I have no idea what's happening here. Based on time. Hopefully you can read that. We're going to move on to the next slide. Alright, last thing. Given f and g and h, find these things. So, I'm going to ask that you pause your video in just a minute. Don't do it yet. And I want you to come back and look at my answers and see if you were able to find h of g of x and h of f of g of x. We're going to leave this one alone for just a minute. So go ahead and pause now. Alright, time to reveal those answers. So, starting with h of g of x, started by taking g of x, which was this square root of 9x minus 4, and I plugged it into h of x. So everywhere I saw an x, I substituted in g of x. Now, I would say you can leave that for right now. You could also simplify that to be 3 times 9x minus 4 all to the 3/2 power plus 5, because the square root gets written as the 2 in the denominator of your exponent. Next one gets a little bit trickier. You are taking g of x, which is this square root of 9x minus 4, plugging it into f of x, which is the squaring function, then plugging it into h of x, which is the 3x cubed plus 5. Again, you can simplify a little bit. This square root and the square are going to cancel each other out. So really you're left with 3 times 9x minus 4 to the third plus 5. You could then multiply that out if you wanted to. Last thing I told you to skip, I want to talk about it real quick, is g of h of 2. So you're going to start by plugging 2 into h, which gives you 29. Well, h of 2 is 29. So instead of saying g of h of 2, you can just find g of 29. It's a substitution that you're making, which ends up being the square root of 257. Remember, f of g of x, or f of g of x. One more operation for you for functions. And those are the 5. Hope you enjoyed.